Welcome back to the Deep Dive. We're the place you come to plunge into complex subjects and really pull out those essential insights you need, to truly get what's happening at the cutting edge.
That's right.
And today, we're diving headfirst into something fascinating, something behind the AI magic we, interact with pretty much every single day. Large language models.
LLMs, yeah. They're everywhere now.
Think about it, right? From writing really compelling emails to answering incredibly complex questions, sometimes even doing this multi-step reasoning that feels, almost human-like.
It's quite remarkable.
LLMs just seem to handle this astounding array of tasks. They're constantly surprising us with their fluency, their adaptability. But here's the burning question, the thing I keep wondering. How did these powerful models, after just being pre-trained on this massive unfiltered chunk of the internet, how do they become so incredibly refined and accurate and aligned with what we actually want?
That's a fantastic question. And it's a bit like discovering a raw diamond. Its inherent potential is enormous, but without that meticulous cutting and polishing, it won't truly sparkle.
Okay.
Pre-training gives these models a vast linguistic foundation. It lets them predict the next word in a sequence with, frankly, astonishing accuracy.
Right, predicting the next word.
But that initial training, while it's absolutely foundational, doesn't inherently equip them for the nuance, the complex, the often ambiguous demands of real-world human interaction. It doesn't just magically make them logical problem solvers or ensure they align with our intentions, let alone, ethical guidelines.
That's a really crucial distinction. So while pre-training helps them predict what word comes next, and that process is based on maximizing the probability of generating correct sequences, this kind of token-wise training, it can sometimes lead to cascading errors, right, if mistakes aren't corrected.
Exactly. Cascading errors are a big problem. The raw model might stumble on what seems like a simple logical task, or maybe produce outputs that are factually incorrect or, just unhelpful.
Right.
Its reasoning, initially, it's largely based on statistical patterns it saw in the data, not explicit logical inference. And that can lead to some, frustrating inconsistencies.
So it knows what words go together, but not necessarily why in a logical sense.
Precisely. The inherent limitation is that while pre-training imparts this vast statistical understanding of language, it doesn't give the model a robust internal model of the world, nor does it instill a sense of human values or preferences. Not automatically, anyway.
Okay. So this deep dive, it's all about that polishing process we mentioned, this sophisticated world of LLM Post-Training. We're going to unpack a really insightful research paper, LLM Post-Training, a deep dive into reasoning large language models, and explore the innovative techniques that sculpt these models, beyond their initial foundational training.
And our mission today, really, is to extract the most important nuggets of knowledge from this pretty complex topic. Give you a shortcut, hopefully, to understanding the cutting edge of LLM development.
Yeah.
We'll explore how these post-training methods let LLMs refine their existing knowledge, significantly improve their reasoning abilities, enhance factual accuracy, and align far more effectively with user intentions and, crucially, ethical considerations.
And just to give you a roadmap for today's exploration, we'll dive into 3 critical categories of post-training.
Okay.
First, fine-tuning. That's really about specializing the model.
Right.
Then reinforcement learning, where models learn from feedback, from experience.
Learning by doing, essentially.
And finally, test time scaling, which is optimizing how models actually think during use.
Which is a really clever idea.
Yeah. So we'll uncover the why and the how behind each of these, discuss the specific algorithms and strategies involved, and look at how they address key challenges like, say, catastrophic forgetting.
Ah, yes. Forgetting old stuff when learning new things. A classic AI problem.
Exactly.
Yeah.
Or how they adapt to entirely new tasks. And most importantly, we'll try and connect it all back to what it means for how you interact with AI, every single day.
Sounds like a plan.
Okay, let's unpack this. Where should we start? Maybe fine-tuning.
Let's do it. Fine-tuning is a great place to start. It's probably the most intuitive step after that initial pre-training.
Right.
It's about taking that broadly intelligent but still very general base model and making it specialized. Like you said earlier, it's like sending a brilliant generalist to a specialized academy.
Perfect analogy.
So the first and often the most critical step in many post-training pipelines is supervised fine-tuning, or SFT.
SFT. Okay.
This process begins with that pre-trained model, and you refine it using a supervised data set. Now, this data set is typically much, much smaller than the pre-training data, but it's exceptionally high quality.
Quality over
Yeah.
quantity here.
Absolutely. Often human-crafted and tailored to specific tasks or desired behaviors. The real goal of SFT is to teach the model a baseline level of compliance with particular formats or styles or instructions.
So making its outputs more predictable.
Exactly. Predictable and usable. It's really the foundational step towards getting the model to behave in a way that matches our explicit expectations. Things like learning to follow instructions accurately or format answers in a specific way.
Okay, so it's about giving it a foundation in, let's say, good manners for specific tasks. But beyond just general instructions, I know many LLMs now undergo what's called dialogue or multi-turn fine-tuning. What's the key difference there? Why is that so important for the kind of conversational AI we use?
That's an excellent point. Dialogue fine-tuning takes the model's refinement a significant step further. It trains it on continuous dialogue, not just isolated prompt-response pairs.
So whole conversations.
Exactly. The data consists of entire chat transcripts, complete with multiple user queries and the corresponding system responses. This is incredibly important for models designed for conversational interactions, like, many of the chatbots we use daily.
Right.
It teaches them to maintain context across many turns, to understand conversational flow, and to produce coherent, context-aware replies. That's what makes the interaction feel much more natural. Now, while there might be some overlap with instruction fine-tuning, because, let's face it, many instructions now come in a chat format,
True.
specialized conversational data uniquely enhances that multi-turn user experience. It lets the model remember what you said 5 minutes ago and actually build upon it.
That really makes sense. It's what stops the AI feeling
Yeah.
just like a search engine spitting out answers and makes it more like a conversation partner.
Okay.
And then there's chain of thought, or COAT, reasoning fine-tuning. This has been a huge buzzword.
Oh, absolutely. COAT is big.
And it feels like a shift from just what the model outputs to how it gets there.
You've hit the nail on the head. COAT reasoning fine-tuning is precisely about teaching models to produce step-by-step reasoning traces, not just spitting out a final answer.
Showing their work.
Exactly. By doing this, they expose their intermediate rationales, their thoughts, if you will. And this is revolutionary for a couple of reasons. First, interpretability. We can actually see how the model arrived at its answer, like looking over its shoulder.
Which is huge for trust.
Huge. And second, accuracy on complex tasks. Things like multi-step math word problems or intricate multi-hop question answering where you need to connect different pieces of information. COAT significantly improves performance there.
So how did that work in practice? How do you fine-tune for that?
In practice, it often involves using human handcrafted supervised reasoning annotations. These literally show the model how a solution unfolds, step by logical step.
Like worked examples.
Precisely. Now, early work, like chain of thought prompting, initially applied this idea just to how we structure the prompts we give the model.
Right. Let's think step by step.
Exactly that phrase. But later efforts, like something called COAT distillation, adapted it to full fine-tuning of the model itself. And this is even extended into multimodal domains now, where models can incorporate images and answer questions with COAT reasoning steps. There's a model called Lava COAT that does this.
Wow.
It's really about teaching the model to show its work, which, just like in school, helps it get to the right answer more reliably.
And speaking of student-teacher paradigms, that brings us to distillation-based fine-tuning. This sounds incredibly efficient.
It is. Knowledge distillation is a really powerful technique. The basic idea is you have a large, powerful teacher model generate labeled data, or sometimes even those detailed rationales we just talked about.
Okay.
And then a smaller student model fine-tunes on this curated data generated by the teacher.
Learning from the master.
Exactly. It's particularly useful because it allows for the creation of lighter, faster models that can retain much of the teacher's performance. Even on challenging tasks where the student might not have direct examples in its own smaller training set.
So it inherits the reasoning capability.
To a large extent, yes. COAT distillation, which we just mentioned, is a perfect example. The teacher LLM generates the intermediate reasoning steps, and the student model is fine-tuned to reproduce both the final answer and that reasoning chain.
Right.
This allows you to get much of the smarts of a big, expensive model without the huge computational overhead of running it directly. There's also something called step-by-step distillation, which generates descriptive rationales alongside final answers, further enhancing the student's learning.
So you get the intelligence without the raw bulk. That's incredibly efficient for actually deploying these things. Okay, wrapping up our fine-tuning discussion for now, we have Preference and alignment, SFT. This seems absolutely crucial for making LLMs, helpful and harmless.
It's a cornerstone, really, for responsible AI development. Now, while it's not purely supervised in its very final stages, we'll get to that with RL, this process typically starts with the supervised preference or alignment fine-tuning stage. Here, human-labeled or human-ranked examples are used to teach the model what constitutes desirable versus undesirable outputs.
Like good answer versus bad answer.
Exactly. For example, safe, polite responses versus toxic or off-topic ones. By explicitly training on these human preferences, the model becomes more aligned with user values and, hopefully, societal norms.
You're embedding values early on.
That's the idea. Instruct GPT, for instance, famously illustrated how vital this supervised preference data is before you even get to the more complex reward model training and reinforcement learning updates. It's about building in our values into the AI's behavior from an early stage, which is why it's so vital for creating trustworthy AI.
That makes perfect sense.
Yeah.
Building in the guardrails from the ground up. Okay, now let's talk about a more technical but incredibly impactful sub-area of fine-tuning. Parameter-efficient fine-tuning, or PEF, and also model compression. I've heard this is a real game changer for accessibility.
You're absolutely right, it is. PFT methods are designed to drastically reduce the computational resources, the compute power, and the memory required for fine-tuning these massive LLMs.
Because fine-tuning a 100 billion parameter model normally takes huge resources, right?
Astronomical resources. So instead of adjusting every single parameter in a model that might have hundreds of billions of them, PFT injects only a small number of new trainable parameters, or it modifies existing ones in a very efficient way.
Okay.
Think of it like tuning a piano. You don't replace every single string, you just adjust the necessary pins.
Nice analogy.
One of the most prominent techniques here is LoRa, which stands for low-rank adaptation.
Laura, I've heard of that.
Yeah, it injects these trainable low-rank adapters, which are basically small matrices, into the existing large model. Only these tiny adapters are actually trained, freezing the vast majority of the original model's parameters.
So you only change a tiny fraction.
A tiny fraction. And this means you can store multiple fine-tuned versions of a model by just saving these small LoRa weights, rather than saving entire copies of the huge base model each time.
That saves a ton of storage.
Massively. And building on this, there's QLoRa. QLoRa combines LoRa with something called 4-bit quantization.
Quantization.
Yeah.
That's making the numbers smaller, right? Less precise, but takes less space.
Exactly. It compresses the model's parameters to incredibly small sizes while still allowing this LoRa-style fine-tuning. This innovation, QLoRa, has made it possible to fine-tune massive models, even those with tens of billions of parameters on consumer-grade GPUs.
Wait, really? Like the ones you might have in a high-end gaming PC?
Potentially, yes, for certain model sizes and tasks.
So you're saying that with QLoRa, for example, I could potentially fine-tune a model the size of, say, a Llama 270B on my gaming rig, rather than needing a supercomputer or a massive cloud budget.
That's the potential it unlocks, yes. It's an incredible leap in accessibility for researchers, developers, smaller companies.
That democratizes things massively.
It really does. It moves LLM customization from being the exclusive domain of large corporations to smaller teams, individual researchers, even enthusiasts. And this is particularly valuable for specialized domains, right? Like medical research, legal analysis, software development, where data might be limited or very expensive to annotate.
Because you can use smaller data sets effectively now.
Exactly.
Yeah.
It makes it far more feasible to use those specific smaller data sets to adapt a general LLM for a niche purpose.
Are there other PFT methods besides LoRa and QLoRa?
Oh yes, quite a few. Beyond LoRa and QLoRa, other methods like sparse GPT focus on pruning, intelligently removing unnecessary connections within the model while trying to preserve its quality.
Like trimming the fat.
Precisely. And libraries like the Hugging Face PFT library, they unify many of these approaches, like LoRa, prefix tuning, prompt tuning, and others, into a single user-friendly framework, which really streamlines their deployment.
Makes it easier for people to use them.
Definitely. And tools like Bits and Bytes enable low-precision training, like 8-bit optimizers and that 4-bit quantization we mentioned, further pushing the boundaries of memory-efficient training. There's also Adalora, which dynamically allocates the parameter budget between different layers of the model.
So it's smarter about where it puts the trainable parts.
Right. And P-Tuning v2, which learns continuous prompt embeddings instead of discrete tokens, offering another efficient way to guide the model without changing the whole thing.
That's truly incredible. It really feels like the next generation of AI tools could be highly specialized, customized to very specific niches, and run efficiently on hardware that's actually accessible.
That's the direction things are moving.
And this fits into that broader ecosystem you mentioned, involving system-level optimizations, data management. It suggests a very holistic approach to making LLMs more efficient and scalable. It's not just about bigger models anymore.
Precisely. It's about smarter ways to adapt them, leveraging every part of the development pipeline.
Okay, now let's shift gears. Let's move on to our second major category, reinforcement learning, or RL, in the context of LLMs. This is where things get really fascinating, I think. Moving beyond just supervised examples to models learning directly from experience and feedback, it sounds like a completely different paradigm.
It is fundamentally different from traditional supervised learning, yes.
Yeah.
In conventional reinforcement learning, you usually think of an agent interacting with some structured environment, right? Taking discrete actions to maximize cumulative rewards.
Like AlphaGo learning to play Go, or
Right.
a robot learning to walk.
Exactly. AlphaGo is a perfect example. Or a robot learning to navigate a maze. But RL in LLMs is adapted specifically for text generation. Instead of a finite action set like move left or place stone, LLMs select tokens, one after another.
Okay.
And the process of an LLM generating text autoaggressively, where each token prediction depends on the ones that came before it, can be effectively modeled as a sequential decision-making problem. We often frame this using something called a Markov decision process, or MDP.
An MDP. Right, that's a mathematical framework for decision-making under uncertainty.
Essentially, yes. It's a framework for modeling decision-making where outcomes are partly random and partly controlled by the decision maker, the agent.
So in the LLM case, the state is the sequence of tokens it's generated so far,
Correct.
and its action is predicting the next token
Mm-hmm. Yeah.
with a reward that somehow evaluates the quality of the entire output sequence at the end.
That's generally the idea, yes. It's a really clever way to frame text generation as this dynamic sequential problem. The LLM's policy, which is just the strategy it uses to choose the next token, is optimized to maximize the expected return, the total reward, over time.
Okay.
Now, a key part of this involves distributing credit or blame back to the individual steps, the individual token choices. This is done using something called an advantage function.
Advantage function, what does that tell the model?
Think of the advantage function as telling the model, how much better was this specific action, this token choice, compared to what we expected you to do in this situation?
Ah, okay. Better or worse than average for that point.
Exactly. It helps the model learn from both good and bad choices it made along the way, even if the overall final outcome was just okay or mixed. And this is crucial because while pre-training helps with fluency, it can also cause those cascading errors we talked about if mistakes aren't corrected over a long sequence.
Right.
RL helps address these limitations. It helps maintain coherence over long generations, especially as models start showing these increasingly complex, emergent reasoning abilities when they're trained on diverse data like code and mathematical content.
That truly makes sense. It's like teaching the model not just to say something, but to say the right thing, step by step, and maybe even understand why it's the right thing over many steps. So what were some of the key foundational RL methods? The ones that laid the groundwork for how we use RL in LLMs today?
Yeah, there were several foundational methods that tackled the early challenges. One interesting one is curriculum learning with Mixer. Yeah, Mixer. It introduces a gradual transition. It starts close to maximum likelihood estimation, which is what the model does during pre-training, just predicting the most likely next word, and slowly shifts towards pure RL.
Ah, easing it in.
Exactly. The overall training loss is a weighted combination, and the weight on the RL component increases over time. This helps the model sort of ease into the RL objective and mitigates the potential mismatch between how it was initially trained and how it's now being asked to learn via rewards.
That's a smart way to bridge that gap between pre-training and RL, making the transition smoother. Okay, what about self-critical sequence training, or SCST?
Ah, SCST. This refines the policy gradient method, which is the core mechanism for how models learn from rewards. It does this by comparing the model's sampled outputs, the sequences it generates, against its own best or greedy predictions.
So comparing against itself.
Yes. Instead of using some arbitrary baseline number, SCST uses the model's own highest scoring output, according to the reward function, as the reference point. If a randomly sampled output performs better than what the model considered its own best guess, it reinforces that pathway.
And if it's worse?
It discourages that sequence. This direct feedback loop ensures that training really aligns with the desired evaluation criteria, like the reward function, rather than just maximizing likelihood. It effectively reduces variance and stabilizes training, pushing the model to continually improve against its own benchmark.
So the model becomes its own internal critic, constantly striving to outdo its previous best. That sounds very efficient. And minimum risk training, or MRT, how does that fit in?
MRT takes a slightly different angle. It directly tries to minimize the expected risk over the output distribution. Risk here is defined by some task-specific loss function.
Like what?
For example, 1 minus the BLEU score for machine translation. BLEU is a common metric for translation quality. MRT incorporates this task-specific loss directly into the training objective. This allows for really fine-grained adjustments of the policy based on how well its outputs compare to a reference translation, directly optimizing for that specific quality metric.
Got it. We've also heard a lot about actor-critic methods like A to C and A3C. How do those fit into this evolution of RL, and why are they important?
Right, actor-critic methods are really fundamental. Traditional policy gradient methods, like the basic reinforce algorithm, can suffer from really high variance. This makes learning unstable and slow, especially with the massive action spaces, all the possible words of LLMs.
Okay, so high variance means the learning signal is very noisy.
Exactly. Very noisy, jumps around a lot. Actor-critic methods were developed specifically to mitigate this. They cleverly combine two components. There's an actor, which is the policy itself, the LLM deciding the next token.
Right.
And then there's a critic, which is a separate function, usually another neural network, that estimates the expected future return or the value of being in a given state or having generated a certain sequence so far.
So the critic predicts how good the situation is.
Precisely. The critic provides a much more stable and less noisy learning signal compared to just sampling rewards directly. This significantly reduces variance in the policy updates and enables more efficient learning. The actor's updates are then guided by that advantage function we discussed earlier. How much better was the chosen action compared to what the critic expected?
Ah, the advantage function comes back.
It does. And modern variants like A2C advantage actor critic and A3C asynchronous advantage actor critic extend this by parallelizing the training across multiple environments or threads, leading to even faster and more stable learning. These foundational methods really establish the mathematical framework for sequential reasoning in LLMs, tackling key issues like exposure bias and that high variance problem.
That's a really powerful combination. It sounds like these early RL methods laid absolutely crucial groundwork, providing initial solutions to the unique challenges of applying RL to language generation. And this then paved the way for the more advanced techniques we see dominating today, particularly those involving human feedback, right?
Precisely. Techniques like large-scale reinforcement learning from human feedback, or RLHF, which often uses that proximal policy optimization algorithm, and advanced reward models like group relative policy optimization, they build directly upon these very ideas. By integrating sophisticated reward signals and leveraging efficient policy updates, contemporary LLMs achieve much improved reasoning, safety, and alignment with human values.
Okay, that brings us neatly to reinforced LLMs and their typical process, often described as having 3 steps. The first step, supervised fine-tuning, SFT we've already covered. That establishes the model's baseline linguistic and factual capabilities.
All right, sets the stage.
Then the second step is reward model training. Can you walk us through that? What happens there?
Absolutely. So after that initial SFT phase, you collect outputs from the fine-tuned model. You give it various prompts, get its responses, and these responses are then subjected to extensive human preference labeling.
This is where the people come in.
This is where the people come in. And it's crucial. Humans are presented with several different generated responses for the same prompt, maybe 2 or 3 or 4. And they're asked to rank them based on quality, helpfulness, factual accuracy, adherence to instructions, whatever criteria you care about.
Sounds labor-intensive.
It is very labor-intensive, but absolutely critical. The reward model is then trained on these human preference scores, these rankings. Its job is essentially to learn to replicate how humans ranked the responses.
So it learns human taste.
Exactly. It becomes a sophisticated judge that can map any given response text to a scalar value, a numerical reward score. And this score then serves as the continuous automated reward signal for the next phase, the actual RL training. This eliminates the need for constant human intervention during the reinforcement learning itself.
So the reward model becomes the AI's internal judge, learning what humans like and dislike, or what's considered correct or incorrect based on those initial rankings.
Okay.
And within reward modeling, I read about something called implicit reward modeling. How does that work? What are the trade-offs there?
Yes, implicit reward modeling is an interesting alternative. It tries to infer rewards indirectly, not from explicit human labels or rankings, but from observed user behaviors or interactions.
Like what kind of behaviors?
Things like upvotes on a forum, acceptance rates of a suggested code completion, click-through patterns on generated summaries, or even just the duration of session engagement. How long did the user keep talking to the chatbot?
Ah, using implicit signals. What's the advantage?
The significant advantage is scalability. You can potentially accumulate vast data sets with minimal direct human labeling overhead because the data is generated organically just from users using the system.
But there must be a catch.
There is a significant risk. The catch is that this approach might inadvertently foster behaviors that exploit these engagement heuristics like click-through rates at the expense of true content quality or factual accuracy.
Ah, optimizing for clicks instead of correctness.
Precisely. It could incentivize clickbait or engaging but maybe misleading content over outputs that are genuinely correct or helpful. That's a key concern when you're trying to build truly reliable and trustworthy AI.
That's a very clear and important trade-off. It highlights just how complex it is to define good behavior for an AI. Okay, and there seem to be two main paradigms for defining how the reward function gives feedback. Outcome reward modeling and process reward modeling. Can you explain the difference? Why might one be preferred?
Sure, outcome reward modeling is the simpler approach. It assigns a reward only at the very end based on the entire generated output. It evaluates the final result, like grading a math test by only looking at the final answer.
Okay, thumbs up or thumbs down on the whole thing.
Pretty much. In contrast, process reward modeling is much more granular. It assigns feedback or rewards, intermediate reasoning steps along the way. It incentivizes coherent, logically consistent, and well-structured chains of thought.
Ah, rewarding the steps, not just the destination.
Exactly. And this approach is particularly valuable for complex tasks like mathematical derivations or generating legal arguments or even debugging code where the path to the answer is just as significant, if not more so, than the final statement.
Right.
Rewarding the individual steps encourages transparency and promotes robust, step-by-step reasoning. It makes the model's internal logic potentially more robust and verifiable.
So process reward modeling is kind of like giving partial credit on a complex problem in school. It helps the model understand where it went right or wrong in its reasoning path, rather than just knowing if the final answer was correct or not. That sounds much more powerful for building genuinely intelligent systems.
It definitely can be. Now, it requires a more complex and detailed annotation process because humans need to somehow label or score those intermediate steps, which isn't always easy.
I can imagine.
But it can often be combined with outcome rewards for a very strong multi-phase training signal. And the hope is that this leads to much more capable and reliable models in the end.
Okay, so once we have that trained reward model, whether it's outcome-based, process-based, or implicit, the third core step is policy optimization. This is where we integrate the reward model into an RL framework to truly optimize the LLM's behavior. And here, the method that seems to come up constantly is proximal policy optimization, or PPO. Why has PPO become such a workhorse for LLM alignment?
PPO is indeed widely adopted, especially for aligning LLMs with human feedback via RLHF. And it's popular largely because it offers a very clever balance between exploration, trying new things, discovering better ways to generate text, and stability.
Stability is key with these huge models, right?
Absolutely. You don't want updates to completely derail the model. PPO updates the policy, the LLM's token choosing strategy, by optimizing a special clipped objective. This objective function basically prevents the policy from changing too drastically from one update to the next.
Keeping the changes small and controlled.
Exactly. And a crucial component within PPO, especially for LLMs, is the KL penalty. KL divergence is a measure of how different two probability distributions are.
Yep.
This KL penalty acts as a regularization term. It ensures that the updated policy stays relatively close to the original base model's policy. This helps retain the base model's linguistic coherence and prevents it from catastrophically forgetting its core language abilities. It avoids the generation of degenerate or just nonsensical outputs while it's learning the new nuances from the reward model.
So it learns the new stuff without messing up the old stuff too much.
That's the goal. This elegant balance between learning and stability made PPO the workhorse of RLHF. It proved that incremental, stable updates were really key to taming the complex, sometimes chaotic learning landscape of large language models.
So PPO is what truly makes reinforcement learning from human feedback, or RLHF, work in practice. Could you maybe break down the entire RLHF pipeline, just recap it from start to finish, and explain why it's considered sort of the gold standard for making LLMs align with our expectations?
Sure, RLHF, as seen in groundbreaking models like InstructGPT and later ChatGPT, refines LLMs through those direct human preference signals. It typically involves three main distinct steps building on what we've discussed.
Okay, step one.
Step 1, supervised fine-tuning, SFT. You take a pre-trained model and fine-tune it on a data set of high-quality labeled examples, often prompt response pairs demonstrating desired behavior. This initial SFT phase establishes strong linguistic capabilities, factual grounding, and basic instruction following, gives the model a good starting point.
Got it. Step two.
Step 2, reward model training. This involves collecting that large data set of human annotated rankings. For a given prompt, humans rank several different outputs generated by the SFT model based on quality. The reward model then learns from these rankings, enabling it to predict human preferences and provide that scalar reward signal we talked about.
The internal judge. Okay. Step three.
Step 3, finally. Policy optimization using PPO. Using the rewards generated by the reward model, PPO guides the updates to the LLM's policy, the SFT model from step 1. This ensures the model continuously optimizes its outputs to prioritize behaviors that are aligned with human preferences, as captured by the reward model.
And PPO keeps it stable during this.
Exactly. Its robustness to potentially noisy or partial reward signals makes PPO well suited for text generation, where nuance and a huge action space are common. It's considered the gold standard because it directly incorporates human value, or at least human preferences, as expressed in the rankings, into the model's behavior, aiming to make it not just smart, but also helpful and harmless.
That's fascinating. Really is a multi-stage process to sculpt these models. But as you mentioned, that human annotation for the reward model is expensive and time-consuming. Is there an alternative to RLHF that tries to scale this process?
Yes, there is, and it's gaining traction. It's called reinforcement learning from AI feedback, or RLA.
RLAF.
Ah.
AI feedback instead of human.
Precisely. RLAIF aims to replace or at least augment human annotation with AI-generated feedback. Instead of relying solely on humans for those preference labels, a secondary, usually highly capable language model, often a larger, more sophisticated one, is used to generate those preference labels.
So one AI ranks the outputs of another AI.
That's the core idea. This AI-generated feedback then trains the reward model, which in turn guides the reinforcement learning-based fine-tuning of the target model, just like in RLHF.
That's the benefit, speed and cost.
Exactly. RLAIF can significantly reduce the cost and time required for data collection, potentially enabling large-scale model alignment without such extensive human intervention. Empirical studies are starting to show it can maintain high performance and alignment, making it a very promising, scalable alternative to RLHF. It could potentially accelerate the development of aligned models dramatically.
It's like having an expert AI tutor teach another AI. Very interesting.
It is, though of course you then have to trust the teacher AI's judgment.
Right, that's a good point. So we're using AI to teach AI, which could massively accelerate development. But there are also methods emerging that aim to skip the complex RL loop entirely, making the process simpler. One notable example I've seen is direct preference optimization, or DPO. How does DPO manage to achieve alignment without the traditional RL infrastructure?
DPO is a really interesting recent development. It trains LLMs directly from human preference data, those chosen versus rejected pairs, without the explicit reinforcement learning loop. That means no separate reward model needs to be explicitly trained first, and you avoid the complexities of policy gradient updates like in PPO.
How does it do that?
DPO directly integrates the human preference signals into the model's training objective itself. The key insight is clever. They realize that an LLM's own log probabilities, how likely it thinks a sequence is, can implicitly represent a kind of reward model. It reflects how preferable the model finds one response over another. So DPO constructs an objective function that directly pushes up the probability of the chosen or preferred response, while simultaneously pushing down the probability of the rejected or less preferred response. And it does this all within a single unified log likelihood framework.
So it's directly tweaking the model's internal taste based on the preference pairs.
That's a great way to put it. It's like directly sculpting the model's internal taste for what's good or bad by adjusting its internal probability scores based on the human preference data. By directly optimizing these log likelihoods, DPO sidesteps many of the complexities of RL-based methods, like training an explicit critic, using advantage functions, or needing that KL penalty and clipping for stability.
That sounds much, much simpler, cutting out a whole layer of complexity. Are there any downsides to DPO compared to PPO? Or why might you still choose PPO in certain scenarios?
That's a fair question. While simpler, DPO might lose some granularity and control. Remember the advantage function in PPO. It quantifies the per-step contributions to the final reward.
Right, the step-by-step credit assignment.
Exactly. That's critical for identifying specific reasoning errors or providing fine-grained credit assignment across a long-generated sequence. This fine-grained stepwise feedback is generally lost in DPO, which tends to treat entire output trajectories more uniformly. So if you need very precise control over the process of reasoning, especially for complex multi-step tasks, PPO might still offer advantages.
Okay, so simplicity versus granular control. What about Oreo? That's another one I saw mentioned. How does it fit into this landscape of preference optimization?
Oreo is interesting because, unlike DPO, it actually reintroduces an explicit value function, similar to the critic in actor-critic methods.
Bringing back the critic. Why?
This allows for more sophisticated strategies, both during training and at test time. For example, at test time, you can use beam search guided by this value function, actively selecting high-value reasoning steps. And during training, it allows for iterative refinement, where failed trajectories identified by the value function can be used to further refine the policy.
So it gives you more insight and control again.
Yes, this explicit value function provides a more detailed, stepwise credit assignment compared to DPO's more implicit approach. It offers more interpretability and control over the intermediate thought process. However,
There's always a however.
right, Oreo's computational cost scales with the length of the trajectory and, of course, the cost of training its separate value model. And its generalization to broader domains beyond the specific tasks it was tested on, like math or agent tasks, still needs more validation. So Oreo offers more control and insight, but potentially at a higher computational cost and complexity than DPO.
Makes sense. Then there's Group Relative Policy Optimization, or GRPO. This one sounds like it's trying to get the best of both worlds. Maybe the power of PPO, but without all its overhead.
That's exactly the aim. GRPO simplifies the PTO framework quite cleverly by eliminating the need for that separate value function, the critic model, which often adds significant computational overhead and memory usage.
So how does it estimate the baseline without a critic?
Instead of learning a critic, GRPO estimates the baseline reward simply by taking the average reward of multiple sampled outputs generated for the same input question or prompt.
Comparing samples against each other.
Yes. This significantly reduces memory usage and can help stabilize policy learning. It also aligns quite well with how reward models themselves are often trained by comparing different LLM-generated outputs rather than trying to predict some absolute value score.
Clever.
GRPO can also incorporate process supervision, providing rewards at each reasoning step, similar to process reward modeling, which helps reinforce high-quality responses in complex, multi-step tasks. Overall, GRPO serves as a more efficient alternative to classic actor-critic frameworks and has been used effectively in models like DeepSeek R1, proving that you can achieve strong results with a more streamlined RL approach.
That sounds like a really powerful optimization for efficiency. Okay, and just quickly, for situations where you might want more diverse outputs or you're actively trying to avoid bias in the model's responses, there's something called multi-sample comparison optimization.
Yes. Instead of just doing pairwise comparisons, this one is better than that one. This approach compares multiple responses simultaneously.
Looking at a whole group.
Right. Given a set of responses for a query, it evaluates each response jointly in the context of all the others. The idea is to capture more nuanced preferences and potentially reduce biases that might arise from only looking at binary comparisons. It's about getting a richer, more comprehensive signal from the human or AI preferences.
Okay, it's clear that reinforcement learning has many different flavors and approaches, constantly evolving to be more efficient and powerful. Now let's look briefly at pure RL-based LLM refinement. Some models are exploring this, sometimes even excluding that initial supervised fine-tuning phase altogether, or integrating it into very specific multi-stage pipelines.
Yes, this approach, exemplified by models like DeepSeek R10 and its sibling DeepSeek R1, represents a really fascinating direction. DeepSeek R10, for instance, aims for a purely RL approach from the get-go. DeepSeek R1, on the other hand, uses a very sophisticated multi-stage pipeline.
What does that pipeline look like?
It includes something they call a cold start data phase, which sounds intriguing, followed by RL training, then SFT, and finally knowledge distillation. It's a very intricate dance of different techniques.
Okay, let's break that down. What does a cold start RL phase involve? Why is that critical if you're trying to lean purely into RL, maybe without a strong SFT base?
This phase seems absolutely critical for stabilizing the model before you unleash full-blown RL training. Without it, you can encounter significant instability that can arise from purely RL-driven updates, especially in the early stages when the model might not have a good policy yet.
So it prevents the model from going off the rails immediately.
That's the idea. It typically begins with gathering a small amount of carefully curated data to essentially fine-tune an initial or base model just enough. This curated data often focuses on capturing human-readable reasoning patterns, generating chain-of-thought-style examples with consistent reasoning processes, and maybe summary fields.
Giving it a template for thinking.
Exactly. This structured format seems to enhance the robustness and interpretability of the model's outputs, giving it a good grounding in how to think, before letting the more exploratory and potentially volatile RL process take over. It provides a stable foundation from which the RL can then learn more effectively.
So it's like setting a strong intellectual foundation before letting the model learn from trial and error.
Okay.
And then there's rejection sampling and fine-tuning mentioned as part of this process. This sounds like quality control.
It is, very much so. This concept is also famously used in models like OpenAI's WebGPT. Once the initial RL training has stabilized the model somewhat, a rejection sampling mechanism is employed.
How does that work?
The model generates a large number of responses for various prompts. These responses are then rigorously filtered, either using automated verifiers or perhaps a strong reward model checking for correctness, clarity, safety, and other quality metrics. Only the high-quality, filtered responses, the ones that pass the check, are then blended with additional data sets to produce a new, larger corpus. And this corpus is then used for a round of supervised fine-tuning.
Ah, so you use the model's best RL-generated outputs to improve it further via SFT.
Exactly. It ensures that only the very best outputs are used for further training, continuously enhancing the model's overall performance and reliability. It's like having the model generate many ideas and then only picking the cream of the crop to learn from, creating this virtuous cycle of improvement.
That makes perfect sense. It's about continually curating its own learning material to get better. And finally, in this multi-stage process, a second RL stage for human alignment. Why another RL stage? Well, after retraining the base model on that combined high-quality data set from the rejection sampling, a second dedicated round of RL can be conducted. The purpose here is often to align the model even more closely with broader human preferences, broader than just correctness.
Yes, things like helpfulness, harmlessness, perhaps creativity, or more nuanced contextual understanding. This is typically achieved by introducing additional reward signals or different prompt distributions designed to capture these broader desiderata. This second RL stage helps ensure the model aligns well with general human values, making it more versatile and contextually aware in various situations. It's part of that continuous refinement loop, driving the model towards ever better alignment and utility.
It's truly amazing how many layers of refinement go into making these models work well. Okay, let's transition now to our third and final major category of post-training methods, test time scaling. This sounds really intriguing because it's about optimization during inference, right? Not during training. It's about squeezing more out of a model that's already trained.
Exactly. Test time scaling, or TTS, not to be confused with text-to-speech.
Right, different TTS.
Yes. This TTS focuses on optimizing computational resources efficiently during inference, or test time, in LLMs. The key idea here is to achieve significant performance improvements without modifying the base model itself through retraining.
How does it do that?
Instead, it allows models to effectively think longer during inference. This happens through structured reasoning steps or iterative refinement processes. And this means that, perhaps surprisingly, smaller models, when equipped with smart inference strategies, can sometimes outperform much larger models on specific, complex tasks.
Smaller models beating bigger ones.
On certain tasks, yes. It's like a smaller, more agile fighter outmaneuvering a huge, powerful battleship through superior tactics, rather than just relying on raw firepower.
That's a huge game changer for deployment costs and accessibility if you don't always need the biggest model. So what are some of the core techniques within test time scaling that enable this?
One of the fundamental techniques which has been around for a while is beam search.
Beam search, okay.
This is similar to a pruned breadth-first search, a common algorithm in computer science. At each step, when the model is decoding, generating text, instead of just picking the single most probable next token, which is called greedy decoding.
Right, the obvious choice.
Beam search keeps track of the top n highest probability partial sequences. These n sequences are called the beam. It explores these n paths simultaneously and discards the lower probability paths that fall off the beam.
So it keeps multiple options open.
For a limited number, yes. By limiting the beam width, n, it manages the otherwise exponential search space while still aiming to find a near-optimal overall sequence. In reasoning LLMs, this allows for systematically exploring multiple plausible reasoning chains in parallel, focusing computational effort on the most promising ones.
And that improves the chance of finding the right answer.
It can dramatically improve the chances of finding a correct and coherent solution compared to simple, greedy decoding, which might get stuck on a locally optimal but globally bad path. It's been traditionally used in tasks like machine translation and summarization, where finding the best overall sentence structure is really crucial.
Okay, so it's about exploring the most likely paths in a structured, intelligent, but limited way. How does that compare to best of n search or BON? That sounds simpler.
Best of n search, or BON, operates quite differently. Instead of incrementally building sequences like beam search, it generates n complete candidate outputs, usually by sampling multiple times from the model.
So n full answers.
Yes. And then it picks the best one among those incomplete answers according to some chosen criterion. This criterion could be a reward model score or even just the model's own likelihood score for the whole sequence. Conceptually, it's an application of rejection sampling at the sequence level. Unlike beam search, which incrementally expands and prunes partial hypotheses, BON simply samples full solutions independently. This allows for potentially greater diversity in the generated outputs, as each sample is essentially a fresh start.
But it sounds more expensive, generating n full answers.
It generally comes at a higher computational cost, yes, because you're generating complete responses multiple times over.
So beam search is maybe about finding the single most probable path efficiently, while BON is more about brute force sampling multiple times to find a high-quality solution, even if it wasn't the single most probable one to generate step by step. Feels like a trade-off.
Precisely. It's a fundamental trade-off. For LLM inference, BON is actually very popular for enhancing correctness or alignment without needing to retrain the model. By sampling multiple answers and selecting the top candidate using maybe a reward model, BON can effectively boost accuracy on tasks like question answering or code generation.
And it's easy to implement.
Relatively easy, yes. And it's almost hyperparameter free, with n, the number of samples, being the main parameter you adjust. OpenAI's WebGPT famously used BON with a reward model to get strong QA performance. And some studies have even shown BON can approach or match RLHF results when guided by a robust reward model.
Wow. Any downsides besides cost?
Well, there's a risk of reward hacking if the reward function you use to select the best answer is imperfect. The model might generate outputs that get a high score but aren't actually good. And there can be instability if n becomes very, very large, as it consumes more compute and might find weird outliers.
Okay, so choosing between beam search and best of n often depends on the difficulty of the question, the desired diversity, and your compute budget. This leads us perfectly to compute optimal scaling, or COS. This sounds like it tries to be smarter about that budget, like a smart thermostat for LLM inference.
That's a perfect analogy. COS is a dynamic method designed precisely to allocate computational resources efficiently during inference. It recognizes that, hey, not all prompts are equally difficult.
Right, some are easy, some are hard.
Exactly. So instead of applying a uniform sampling strategy like generating n samples for every single prompt, COS intelligently categorizes prompts into difficulty levels, maybe easy, medium, hard.
How does it know the difficulty?
It could use ground truth success rates if you have them from testing, or more practically, it might use the model's own predicted difficulty or confidence for the prompt. Once categorized, the strategy adapts the compute allocation.
Oh.
Easier prompts might undergo something like sequential refinement, where the model iteratively refines its initial output, requiring less overall computation because it's probably close to correct already. Harder prompts, on the other hand, might trigger more intensive parallel sampling, like best of n, or maybe a wider beam search, to explore multiple variations. It ensures the model dedicates resources where they're most needed.
That's incredibly smart. It balances exploration for the challenging inputs and just refinement for the near-correct responses, so it optimizes performance per unit of computational effort.
Exactly, and remarkably, the paper suggests this method can achieve something like 4 times lower compute usage than traditional best-of-n sampling, while maintaining equivalent performance on some benchmarks. It avoids wasting resources on trivial cases while ensuring sufficient sampling diversity for complex tasks. This is a huge potential leap in efficiency for real-world deployments of LLMs.
Wow. Okay. And how does chain of thought prompting reemerge here? We talked about code fine-tuning earlier, but now it's showing up as a test time strategy.
That's a great question, and it highlights the versatility of the code idea. While code formats can definitely be used for supervised fine-tuning to reshape how the model responds, Code prompting itself is a powerful inference time strategy.
The let's think step-by-step thing again.
Exactly. It's about prompting the model in a way that encourages it to generate those step-by-step reasoning traces at the time of inference. Wei and colleagues famously demonstrated its effectiveness on arithmetic and logic tasks just by adding that simple phrase. What's almost magical is that even just adding let's think step by step, which is known as zero-shot Code, can trigger coherent multi-step reasoning in sufficiently large, well-pre-trained models without any specific code fine-tuning.
That's amazing. Just the prompt changes the behavior.
It seems to unlock latent capabilities. Subsequent work then combined Code prompting with sampling-based strategies like self-consistency for even higher accuracy. So it's a lightweight yet incredibly effective way to unlock deeper reasoning right at the moment of inference, just by asking the right way.
That simple phrase, let's think step by step, can unlock deeper reasoning, truly remarkable. Okay, building on that, what is self-consistency decoding? It sounds like it leverages that multipath thinking Code enables.
It does, brilliantly. Self-consistency is a decoding strategy that builds directly upon Code prompting, instead of just generating and following one single reasoning path to an answer.
Which might be flawed.
Right. Self-consistency samples multiple distinct reasoning paths for the same given question, often by using Code prompting, but with some randomness introduced, like higher temperature sampling.
Okay, so it gets several different ways of thinking about the problem.
Exactly. Then, it aggregates the results from these different paths, often by simply looking at the final answers produced by each path, and selects the answer that is the most consistent across all the sampled paths. Typically, this is done by a simple majority vote.
Ah, like crowdsourcing the answer from within the model itself.
That's a perfect way to describe it. It allows the model to think in many ways, and then trust the consensus, much like gathering multiple expert opinions. And this dramatically boosts correctness in many complex reasoning scenarios, like arithmetic or common sense reasoning.
And it doesn't require new training.
No new training needed. Its strength lies in requiring only extra sampling compute at inference time, making it a popular and efficient test time scaling strategy to obtain more reliable answers from existing LLMs. It's even been extended to something called universal self-consistency for more general generation tasks beyond just finding a single final answer.
That's brilliant. It's like an internal peer review process for the AI's thoughts. Okay, and then we have tree of thoughts, or TOTI.
Yeah.
This sounds like an even more sophisticated approach to exploring reasoning paths than just linear chains or multiple independent chains.
It is. Tree of thoughts, or TOTI, generalizes the chain of thought approach. It allows the model to explicitly branch out into multiple possible thought sequences instead of just following a single linear chain.
Building a tree structure.
Exactly. It frames the problem of LLM reasoning as a search through a tree structure, drawing inspiration from classic AI search methods like breadth-first or depth-first search. Intermediate reasoning steps are treated as nodes in this search tree. From a given state or node, the LLM is prompted to expand possible next steps, or thoughts. So instead of sampling just one long reasoning path, the model explores a tree of branching thoughts. And critically, it can perform look-ahead and even backtracking if a particular path looks unpromising.
So if one line of reasoning leads to a dead end or seems like a poor intermediate result, the model can actually return to an earlier point and try a different branch. That really mimics how a human problem solver might approach a complex puzzle.
Precisely. At each step in the tree, the LLM might generate several candidate next thoughts. Then, some heuristic, or maybe a value function, evaluates the promise or quality of each partial solution represented by a node. A search algorithm then navigates this tree, intelligently deciding which branches to explore further based on these evaluations.
So it's an iterative prompting procedure.
Yes, where the model generates thoughts, evaluates them, and refines its approach based on the tree structure. It has shown significant enhancements in performance on complex reasoning tasks that require exploration and planning. It can even allow for collaboration between multiple LLM agents potentially working on different parts of the thought tree.
That's incredibly powerful. And it leads directly, it seems, to graph of thoughts, or GOT. How does that extend the capabilities of TOT? If TOT is a tree, GOT is a graph, more connections.
Exactly. Gati is presented as an evolution of TOT, aiming for even greater flexibility and efficiency. While TOT structures reasoning as a tree, which has fairly rigid parent-child relationships.
Right, branches don't typically merge back together in a tree.
Correct. Gati represents thoughts as nodes in a more general graph. This allows for much more flexible dependencies and interconnections between thoughts. A potential limitation of TOT is its somewhat restricted backtracking. Once a branch is pruned or discarded, it's not easily reconsidered. Gati aims to overcome this by allowing more iterative refinement. Previous thoughts can be revisited, modified, and improved upon based on later steps. It allows for cycles and more complex dependencies between ideas, maybe combining insights from two different branches.
So you can merge promising ideas from different lines of reasoning.
Potentially, yes. This iterative nature, the ability to revisit and combine, is especially useful in complex reasoning tasks, where initial thoughts might need adjustment based on later insights. Gati also claims significant improvements in computational efficiency compared to 2T by reducing redundant calculations through the merging of equivalent partial solutions. It aims to be superior for tasks requiring truly complex reasoning by allowing for these more dynamic and interconnected thought processes.
So Gati offers even more flexibility and potentially efficiency than 2T, leading to perhaps even more robust problem solving.
Okay.
Another intriguing approach mentioned is confidence-based sampling. This sounds like the model itself is assessing its own certainty about things.
Yes, that's exactly the idea. In confidence-based sampling, the LLM generates multiple candidate solutions or reasoning paths, but then it prioritizes or selects among them based on the model's own internal estimate of its confidence in each outcome.
How does it estimate confidence?
It can happen in a couple of main ways. One way is simply by selecting the output with the highest log probability score, the one the model thinks is most likely. This is essentially like best of n, but using the model's own highest confidence as the selection criterion.
Okay.
Another way is through guided exploration. For instance, in a tree search like 2T or GOT, the model's token probabilities, its confidence in the next step, can be used to decide which branches to expand first, prioritizing exploration down higher confidence paths.
So it focuses effort where it feels more sure.
Right. Compared to pure random sampling or uniform exploration, this biases the process towards what the model believes is most likely correct, potentially reducing wasted computational effort, exploring low likelihood paths that are probably dead ends.
So the model is essentially asking itself, how sure am I about this? And using that answer to guide its thought process. That really is a form of self-reflection.
It is, in a computational sense. Confidence-based strategies are used at inference time, for example, to assign confidence scores to possible completions in a tree-based search, guiding the exploration, or sometimes to decide when to halt reasoning altogether, or maybe even ask a clarifying follow-up question if its internal confidence score is below some threshold.
That's fascinating, deciding to ask for help when unsure.
It's a step towards more robust interaction. It's also used in ensemble settings sometimes, where maybe a secondary model is trained specifically to evaluate the confidence of multiple answers generated by the primary model.
Okay. And closely related, it seems, is search against verifiers. This sounds like having a built-in quality control system during inference.
It is exactly that, a powerful quality control mechanism applied at inference time. This approach aims to enhance answer quality by generating multiple candidate responses and then selecting the best one using some kind of automated verification system.
Not just relying on the model's own confidence or probability.
Right. It shifts focus from merely increasing pre-training compute to optimizing test time compute, allowing models to think longer or perhaps check their work during inference through structured reasoning or iterative refinement against a verifier.
What are the steps?
It typically involves two main steps. First, a proposer model, The main LLM generates multiple candidate answers or reasoning paths, often using high-temperature sampling to encourage diversity.
Okay, get lots of options out there.
Then second, a verifier evaluates these candidates. This verifier could be a reward model trained on correctness, or another specialized LLM trained to critique, or even potentially a symbolic reasoning system or external tool like a calculator or code interpreter. It checks the candidates based on predefined criteria like correctness, coherence, factual accuracy, or alignment with desired processes.
So the verifier acts as an external critic or fact checker.
Exactly, ensuring higher quality output by filtering out the flawed proposals.
Finally, in this test time scaling category, we have Monte Carlo tree search, or MCTS. This algorithm really gained prominence with AlphaGo, didn't it? How is it being adapted for LLMs?
Yes, MCTS was absolutely central to AlphaGo's success in mastering the game of Go. It's a sophisticated stochastic search algorithm that builds a decision tree by performing many random simulations or rollouts.
Okay, how does that apply to text?
In LLM reasoning, we can treat the generation of text as a sequential decision process, just like moves in Go. Each possible next reasoning step or word or token can be thought of as an action available at a node in this decision tree.
And the simulations.
A simulation or rollout involves letting the LLM continue to generate text from that point, perhaps randomly or using its default policy, until a final answer or outcome is reached. A reward could then be assigned based on whether that final answer is correct or helpful or leads to a desired state.
So you play out many possible futures from a given point.
Exactly. By repeatedly doing this, selecting a path, simulating to the end, getting a reward, and updating the statistics for the nodes along that path, MCTS can identify which initial chains of thought or intermediate steps have the highest empirical success rate based on these simulated rollouts. It's powerful because it can handle very large search spaces by intelligently sampling, balancing exploration, trying new things, and exploitation, following promising paths, naturally incorporating uncertainty to find potentially optimal paths.
So it's like a strategic planner for text generation, simulating future outcomes to make better decisions about the next step in the present. That sounds incredibly deep.
It is, and recent efforts are actively integrating MCTS with LLMs for complex reasoning and decision-making tasks. For instance, one approach called Monte Carlo Thought Search uses MCTS to guide an LLM to ask a series of sub-questions needed to find an answer, treating the LLM itself as the environment to explore. MCTS has also been successfully applied to tasks like code generation, where the algorithm explores different potential code structures and function calls. Early results show MCTS-based reasoning can solve problems that simpler single-pass or greedy methods often miss.
What's the downside? Compute cost again.
It typically requires significantly more compute during inference than simpler methods, yes. Research is ongoing to improve its efficiency, maybe by combining it with learned value functions or heuristics. But in essence, MCTS enables an LLM to effectively look ahead through simulated rollouts and make more informed strategic reasoning choices, much like it did for AI in complex games.
This brings us to a really important discussion: the trade-offs between pre-training and test time scaling. They both aim to improve LLM performance, but they do it very differently, with distinct costs and benefits.
They are indeed distinct yet ultimately complementary strategies. Pre-training, as we know, involves scaling up the model parameters, the size of the model, or increasing the amount of training data. This requires substantial upfront computational investment, often hundreds of millions of dollars, for the largest models.
Building the foundational brain.
Exactly. It establishes the foundational, broad linguistic understanding and world knowledge capabilities of the model. In contrast, test time scaling optimizes the inference time compute through methods like iterative refinement, like COS, search-based decoding, like beam search, MCTS, TOT, or adaptive sampling, like best of N. This allows for performance improvements without modifying the base model itself through retraining and without those massive retraining costs.
So pre-training is about building a bigger, potentially smarter brain from scratch, investing huge resources up front, while TTS is about using that existing brain more cleverly and efficiently at the moment you need to solve a problem. It's optimizing the thought process itself.
Precisely. That's a great summary. From a performance versus cost perspective, the research suggests TTS strategies can sometimes achieve results comparable to a model maybe 10 or 14 times larger, at least on easy to intermediate difficulty tasks, like certain math benchmarks.
Oh, 14 times larger.
That's what some studies indicate for specific tasks and metrics, and it can also reduce inference costs, sometimes by 4 times fewer FLOPs, floating point operations, in compute-intensive scenarios compared to just using a much larger model naively. This means you can potentially get more bang for your buck with a smaller, efficiently deployed model using smart TTS.
But pre-training must still have advantages, right?
Oh, absolutely. Pre-training often remains superior for the hardest, most general tasks that require deep, broad reasoning capabilities not easily replicated by search at inference time. Or when inference compute constraints are very tight and you simply need the answer fast from a model that has the knowledge deeply encoded. Larger pre-trained models inherently encode deeper, broader reasoning capabilities.
So for foundational broad capabilities and maybe speed on diverse tasks, pre-training is key.
Yeah.
But for refining and optimizing context-aware responses on specific, complex problems, especially if you have a flexible inference budget to think longer, test time scaling really shines. It sounds like the future will involve cleverly combining them.
Yes, absolutely. They are definitely complementary. The future of LLM systems will almost certainly adopt a hybrid approach. You might have smaller, more cost-effective base models pre-trained with essential knowledge, while test time scaling dynamically enhances responses through adaptive on-demand computation when needed for harder problems.
The best of both worlds.
Exactly. This kind of synergy enables more cost-effective, efficient, and versatile large-scale model deployment.
Okay. Now, to evaluate all these sophisticated post-training phases, SFT, RL, TTS, we need robust benchmarks. What are the key areas of evaluation that researchers use to actually measure progress in post-training?
That's crucial. You need good measurement. A diverse set of benchmarks is vital to comprehensively assess LLMs after post-training. These benchmarks cover everything from raw reasoning power to alignment with human values, multilinguality, and general comprehension. They're crucial for guiding the fine-tuning process, calibrating models, and optimizing them across these various stages.
So what are some examples? Let's start with reasoning.
Okay, reasoning benchmarks specifically assess LLMs on their logical, mathematical, and scientific reasoning abilities. This includes well-known datasets like math, GSM-8K for grade school math word problems, and MetaMath QA, which focus on complex problem solving. Then you have things like WorldTree v2 for scientific question answering, or MMMU, which is a massive multimodal benchmark requiring understanding of both text and images. And PandaBench extends this further into multilingual reasoning, making sure models can solve problems effectively in different languages, not just English.
Right, assessing core intelligence across domains and languages. And then, critically important for post-training, there are RL alignment benchmarks. These seem central to ensuring models are helpful, harmless, and actually aligned with what users want.
Absolutely vital. These benchmarks evaluate how well models refine their response generation based on feedback, how well they adhere to ethical constraints or safety guidelines, and generally how well they produce user-aligned outputs through processes like RLHF or DPO.
What do these look like?
Datasets like HelpSteer and UltraFeedback evaluate models based on multi-attribute scoring, looking at helpfulness, honesty, harmlessness separately, and their alignment with user instructions, offering more nuanced feedback than just a single score. Anthropic's HHRLHF, helpful and harmless RLHF dataset, and benchmarks like PKU Safer LHF specifically explore how well models adhere to principles of harmlessness and helpfulness, really probing safety-critical aspects. And there are also benchmarks like Natural Instructions v2 that test very granular instruction following, making sure models don't just understand the gist, but execute complex instructions reliably. It's a continuous effort to ensure these powerful AIs are being developed and refined responsibly.
It's clear that the field is constantly evolving, with new techniques and new benchmarks emerging all the time. Looking ahead, what are some of the most exciting future directions for LLM post-training that researchers are focusing on right now, based on the trends?
Well, looking at the research trends outlined in the paper, we've definitely seen a noticeable increase in the prominence of RL techniques for refining LLMs, particularly since around 2020. And within RL, there's a strong focus on human-in-the-loop RL methods.
Like RLHF and its variants.
Exactly. This emphasizes the growing demand for interactive approaches and achieving scalable alignment with human preferences. Reward modeling itself has also seen a steady rise in interest, driven partly by the emergence of self-rewarding language models and techniques like RLAIF.
But are there major challenges still?
Oh, definitely. The field still struggles significantly with reward hacking. This is where models find clever, unintended ways to exploit the reward function to maximize their score without genuinely achieving the desired behavior or outcome.
Like a student learning to game the test instead of learning the material.
Precisely. Designing truly robust, failure-aware reward functions that are difficult to game remains a critical, ongoing challenge. How do you specify goodness in a way that can't be easily exploited?
That's a fundamental challenge. Making sure the models are truly good at the task, not just good at manipulating the reward signal. It's like teaching the AI genuine integrity, almost.
Indeed. Beyond that, those decoding and search methods we talked about, tree of thoughts, Monte Carlo strategies, they're continually improving LLM reasoning and decision-making. But these techniques often demand reliable uncertainty estimators to prevent excessive computational overhead.
Why uncertainty?
Because if the model isn't sure how confident it is about a path or how promising it is, it might overthink exploring too many branches unnecessarily, wasting compute. Knowing when to stop searching is key.
Makes sense.
Furthermore, safety, robustness, and interpretability have really become central concerns for the entire field now. Research is increasingly focused on things like bias-aware and uncertainty-aware RL, and particularly mitigating catastrophic forgetting.
Right. The problem where models degrade their base capabilities, their general knowledge, when you fine-tune them too much with RL on new specific tasks.
It's a persistent problem. How do you specialize without losing generality? We're also seeing increasing activity in areas like personalized reinforcement learning, adapting models to individual users, and on-device adaptation, as LLMs start moving closer to individual users and edge devices, away from giant data centers.
So a lot of focus on making models not just powerful, but also safe, reliable, efficient, and adaptable to individual needs. What about that overthinking phenomenon you mentioned earlier in the context of uncertainty? That sounds like a subtle but potentially significant efficiency problem.
The overthinking phenomenon is indeed a key challenge highlighted, especially for reasoning LLMs using methods like chain of thought. Analysis reveals that potentially up to, say, 22% of computation can be wasted in generating reasoning chains that exceed the optimal or necessary length for a given problem.
So the model just keeps writing steps even after it could have reached the answer.
Essentially, yes. Models sometimes generate excessively long chains of thought, which not only reduces token efficiency, making interactions slower and more expensive, but significantly increases deployment costs, often without actually improving the final answer quality. It's like a human trying to solve 2 plus 2 by writing out pages of unnecessary lemmas and proofs.
Okay, I see. So what are the potential solutions?
Future research is looking into solutions like partial rollout strategies in search, maybe better length penalty mechanisms in the reward function or decoding, and potentially hybrid architectures that intelligently combine methods. For example, maybe using NCTS for initial exploration, but switching to something more efficient like GRPO once a promising direction is found. It's about finding better exploration-exploitation trade-offs, making models smarter about how long they actually need to think to reach a confident solution.
That's a great example of refining the process of reasoning itself, not just the outcome. So the overall vision for future LLM systems seems to be about intelligently combining all these diverse methods we've discussed, SFT, PEFT, RL variants, TTS strategies.
Precisely. We'll likely see increasingly sophisticated hybrid frameworks, maybe initializing RL policies with knowledge distilled from larger models, combining the exploratory benefits of RL with the stability and knowledge grounding from supervised learning or distillation. Curriculum sampling strategies that progressively increase task difficulty during training, while maybe using distillation to preserve linguistic coherence, will also likely be key. Parameter-efficient fine-tuning methods, like LoRa, could be leveraged during RL updates to maintain base capabilities while efficiently enhancing reasoning on specific tasks. So mixing and matching. Exactly. For instance, one promising direction mentioned is combining process reward modeling guided tree search, like 2CAR-T with process rewards, with online distillation. This could potentially achieve significant efficiency gains while maintaining high accuracy on complex datasets like math. It's truly becoming a holistic field, combining the best of all these worlds to create AI that is hopefully intelligent, adaptable, efficient, and aligned.
That's truly fascinating. Wow. Okay. We've really taken a deep dive today into the complex and I think often surprising world of LLM post-training. We've moved from the broad strokes of that initial pre-training to the meticulous art of fine-tuning, the experiential learning we see in reinforcement learning, and those clever optimizations of test time scaling. We've really seen, I think, that the magic isn't just in making models bigger, although that's part of it, but crucially in making them smarter and more aligned with human intent through these post-training steps.
Absolutely. And maybe to recap some key takeaways from our exploration today. First, and maybe most importantly, post-training is absolutely crucial. It's the alchemy, if you will, that transforms LLMs from just having broad linguistic understanding into precise, ethical, and highly capable tools that can perform complex reasoning. It fundamentally addresses the inherent limitations of raw pre-training, giving models purpose and precision.
Yeah, couldn't agree more. Second takeaway for me is that reinforcement learning is really central to this evolution, especially with techniques like RLHF and maybe increasingly RLAIF. RL provides this powerful mechanism for models to learn directly from feedback. It optimizes their behavior for human preferences and helps them tackle complex multi-step tasks. We saw its growing prominence in the research trends, particularly with human loop RL and things like process reward modeling, which pushes models to think more logically step by step.
Third, test time scaling is a true game changer. It really demonstrates that sheer model size isn't the only path to high performance. Techniques like tree of thoughts or compute optimal scaling allow smaller models, equipped with smart inference strategies, to punch far above their weight, sometimes outperforming much larger models on specific tasks. It's all about optimizing the thinking process at inference time, not just during training.
Right, brains and smarts. Fourth, and this underlies everything, the entire LLM ecosystem is interconnected. As we saw in the various frameworks and how methods build on each other, efficient LLM development is truly a holistic approach. It's not just about one silver bullet technique. It combines system optimizations, meticulous data management, and diverse model strategies, SFT, RL, TTS, to achieve those breakthroughs.
And finally, we highlighted some persistent challenges, but also exciting future directions. These include ongoing issues like catastrophic forgetting, that tricky problem of reward hacking, and the efficiency drain from the overthinking phenomenon, but also very promising areas like hybrid frameworks combining different techniques, personalized adaptation for individual users, and critically, an increasing focus across the research trends on ensuring safety, robustness, and interpretability.
So what does this all mean for you, the listener, the user, interacting with these systems? It means that the AI you interact with, whether it's helping you generate an email, brainstorming ideas, summarizing a document, or answering complex questions, is constantly being refined. It's being worked on to be more accurate, more helpful, and more trustworthy.
That personality you might perceive, or the intelligence, it isn't just magically built in from absorbing vast amounts of data. It's carefully sculpted through these advanced post-training techniques we've been discussing.
Yeah. And it means a future where AI isn't just about raw power or scale, but hopefully about intelligent, adaptive problem solving that's tailored to specific needs, maybe becoming more like a reliable, thoughtful partner in various tasks.
And that leads to a final, maybe provocative thought for everyone to mull over. If these sophisticated post-training methods are making LLMs capable of increasingly complex, multi-step reasoning, even allowing them to think longer, like with TOTI or MCTS, and refine their own outputs, what new frontiers will that open up in human-AI collaboration? What becomes possible when your AI partner can truly think through a problem with you?
And conversely, how will our own reasoning and problem-solving habits evolve? As we increasingly rely on partners that can seemingly think step by step alongside us, does it change how we approach problems ourselves?
Food for thought.
Definitely. Well, that wraps up our deep dive into the fascinating world of LLM post-training. We hope this exploration has given you some surprising facts and maybe plenty of aha moments to chew on.
Hopefully demystified some of the magic.
Until next time, keep exploring, keep learning, and keep asking those deep questions.